Yeah.
Okay. So now that you're all here, let's just start with the second talk of today. Aru is going to tell us about something great.
No pressure. Thanks. Thank you for returning. Anything we should talk about before we start back up? Didn't receive any feedback. This sound.
Oh, I clicked the link and it didn't work.
Oh.
The one inside of the document didn't work.
Ah, that's interesting. Did you try the one that was on the board?
Did they match?
He couldn't click on it.
After the lecture, I will try to fix that. I'm sorry. It was not my goal to give you an inactive link in some sort of weird way, but I will fix that. Thank you. That is excellent feedback.
Also, your talk was great.
That's also excellent feedback. Highly encouraging. Okay. Right. Okay. A couple of people did send me some homework solutions. That was great. Please keep them coming. I did incorporate them. I incorporated the solution as well as some more figures and notes into the lecture notes, so it was very recently updated. I'll keep working on that, especially this afternoon. Figures take a long time to make. So for example, if you are drawing nice figures on your tablet, you could also send me those, and then that will help everything move faster. That would be great. All right. Today we're going to keep doing this. Recall this was our goal. This results of Lee and Moshinsky. We had made a lot of progress. We had started off with our primitive class. We had represented that class alpha by some map F of a generically immersed sphere inside of my ambient for manifold M. And we had found these disks bounded by these nice so-called Wiki circles. I rushed through the end of the proof yesterday, so I decided that I would prefer to tell you what happened rather than move on to something else, because that seems silly. So today I want to there'll be a bit of repetition of what I sort of rushed through at the end of yesterday, hopefully with more clarity. That's at least the goal. This was the status of our proof. We had talked about if we were, very, very lucky, we would have been able to find some very nice Whitney disks, but unfortunately the reality did not match our dream. The reality had all sorts of problems. There were 4 types of problems that we discussed. And we also had these very geometric maneuvers that we could use to try to solve those problems. But unfortunately, those solutions came with their own costs. And we noticed that you could try to fix one problem, but that might create some more problems of a different type and so on. So in particular, one thing I really wanted you to notice is that these problems are not independent of one another. You can trade them off for each other, as you can see in the cost column. And then this really is, we'll have a lot of details that you will forget, I promise. Unfortunately, it's just impossible to remember all the details. But I really hope that one thing you'll keep in mind is these are extremely explicit. And this proof technique really comes down to, I have my geometric maneuvers, and I'm going to try to do them in a clever way in the right order so that I could solve all my problems. I didn't manage to draw the boundary twisting. I won't. Daniel drew a picture yesterday. You can find these in books. Happy to talk about it more, but not enough time. But I would rather tell you about this, the first thing. I had said at the end of yesterday that the solution for this first type of problem is the disk embedding theorem. And in particular, there's no cost for using it. This is actually free. So today I want to start off by telling you how to use the disk embedding theorem to arrange for this. Free is sort of a relative term. It's free in the sense of we now get to use it. It's not free in the sense of this embedding theorem was hard to prove, a lot of time and effort went into that, but we are the lucky generation that can just use it. So it's free for us. I want to say very explicitly what I mean by it though. So here's my explicit claim. The claim is that if you have all of my twisting numbers are 0, all of the boundary intersections have been fixed. And the Whitney disks don't intersect the Fs at all. Then there exist Wi bar, which are now locally flat embedded disjoint Whitney disks. With interiors in the complement of F. So I'm going to prove this claim for you in a second, or at least I'm going to outline it. But the thing that I would like you to see is that if I have this, then I win. Because what this is telling me, these conditions on these Whitney disks that I've written down, these are Whitney disks for these intersections of F with itself. I'm just saying I can take whatever Wi's I had, can throw them out, I can find better ones. And the better ones are precisely what I wanted in my dream scenario, right? There were the ones where I could now do the Whitney move. When I do the Whitney move, all of these intersections will be resolved. I didn't say anything about G, but I'm not trying to do anything with G. So I just win. In fact, I win a bit too much because I get an embedded sphere, right? So if I could manage this, then I don't need genus 1. I can get a spherically embedded representative. Is that part clear? Right, so this is what I mean when I say like the issues of the first type can be resolved by free, because you're just saying if you can solve the other 3 types of problems, then you can solve the first type and then you'd be done. And like, how will I prove this claim? This will be by the disk embedding theorem. That's why I wrote that at the top. Well, we'll apply it to my original collection, Wi. These Wi's are disks. They're immersed disks that wish to become embedded, right? They're part of my input to the disk embedding theorem, but I really want those embedded disks to live in this complement. By assumption, these guys do live in the complement. So I'm going to apply this thing in the ambient manifold complement of the Fs. So right, these input guys live there, and I'm hoping that the output guys will also live. Is that reasonable? We have to check the hypotheses of the disk embedding theorem. That's the rest of the proof of the claim. But does this make sense? So what were the conditions of the disk embedding theorem? So let's check them. What do we need? Well, the first thing I needed is I only stated the disk embedding theorem for you in a simply connected Four manifold. M is simply connected, but it's not obvious that M minus nu of F is simply connected. Nu of F means normal bundle, in case that was. So the first thing I have to do is to make sure that this complementary region actually has the right pi1. You guys will do that for me later today. You'll prove that this is isomorphic to pi1 of M. And the key reason for why that's true is because of this friend G that I have over here. So this is because of G. And you should think about this because it's an exercise, but one thing to consider is like ambient manifold is simply connected. So all loops are null homotopic. I'm trying to make loops null homotopic in the complement of F. problems would be that those null homotopies might intersect F. They only intersect in like meridians of F. But at any time you have this meridian, you can tube into G to push it off. So I've solved the exercise for you, but think about this more because it's really important. So G is a very good friend. G helps you in the table. G also helps you here. Okay. So the pi1 is fine. But since we're talking about friends, the other thing we have to check in the disk embedding theorem is that I can't just have disks. I need the disks to come with their own friends, right? So I need algebraically dual spheres for these W's. This is where the Clifford torus will come in. So I have to quickly remind you what the Clifford torus looks like. For any given W, I need to find you an algebraically dual sphere. And well, a W is pairing up 2 points of intersection. So I'm just going to look at one of those points of intersection. And I'm going to look at the Clifford torus there. We agreed that there's a Clifford torus at every transverse double point singularity. I'm going to first draw it in an annoying way. I'm going to draw it as these 4 points. And now I'm going to draw it in a better way over there. That's this Clifford torus P. So we've drawn the Clifford torus before. Let's draw it again very quickly. Clifford torus is orange. This is just repeating what was there before. Yeah, remember the Clifford torus? Where is the Whitney disk in this picture? The Whitney disk, which is in green, was pairing that point of intersection. So in that picture, it's kind of going to show up as this little sheet that lives right there. And in green over there, I've shown you part of that Whitney circle, the boundary of the Whitney disk. I believe that that's where the Whitney disk would be, like sort of standing vertically on top of that flat bit. And what we notice is that the Clifford torus, T, that intersects my Whitney disk at precisely 1 point. So Ti maybe. So Ti and Wi are geometrically dual, meaning that they intersect at a single point. There's a problem, notably a torus is not a sphere. So we have to somehow, we have a torus, it's very nice, but I really need a sphere. So I need to somehow change this guy into a sphere. I'm gonna call upon your friends. You have some friends around. In particular, I have my G. So let me draw G in the picture. G looks something like this. And I have my torus. That circle over there is one of these circle factors of the torus. Is this visible? I don't know what to do about this. It's like I've drawn the meridian of the torus. That meridian bounds a little disk. That disk intersects F at a single point. See it, right? It's just like right there. I don't want it to intersect F. I'm looking for an algebraically dual sphere in the complement of F. But I know how to fix those things. I tube into G. So I take that little disk and I take a little tube and I tube into my friend G. And now I have a disk bounded by that circle in the complement of F. Yeah? How are you doing? Thumbs ups? Any thumbs downs? Okay.
Why is it embedded?
It's not embedded. I never said it's embedded. Good question, trick question, not embedded. G is not embedded, right?
Are you tubing it off twice or?
Right now, I haven't made it into a sphere yet,
Oh,
but you're seeing the second step. So what I've found for you right now is there's some disk, some immersed disk bounded by that circle. Now I'm going to cut my torus along that circle, glue in 2 copies of the disk, and then the result will be a sphere. Does that make sense? Does that make sense? This will be much clearer if that disk were embedded. Then you cut along it, you get an embedded sphere. But it's not embedded. It's potentially super immersed. And it's still a sphere that you get in the end, just a super immersed sphere. And that's fine. My algebraically dual sphere didn't need to be embedded. It just needed to be immersed.
And G also might intersect W.
G also might intersect Wi. And in particular, that's why I only get an algebraically dual sphere and not a geometric dual sphere. Because if G were not intersecting the W's, then it would be geometrically dual. T was geometrically dual, and I did this modification along disks disjoint from it, it would still be geometrically.
So
I'm jumping the gun. Can I just write down what I just said in words in case anyone is lost? So I have this circle bounding this disk. I'm going to take a parallel copy. So cut the torus along that circle. You get 2 copies of the circle. It's a little annulus. And then cap off those 2 circular boundary components by 2 copies of that disk. So in the ideal situation, so in the abstract situation, what you're doing is this. You cut along that thing. So you would get a picture like that in the abstract situation. So you might think about you've taken this model and immersed it in the 4 manifold, in the complement of F. Right. There were questions, I ignored them, but now I'm back. What
I
were they?
answered my question.
Daniel answered his own question. Excellent, self-answering question. Mark?
Does the framing matter, or is it just gonna, if the framing's messed up, will it just give you more double points so you don't care, and it's like that?
That's a great question. So I said algebraically dual sphere, but I needed things to be true for that algebraically dual sphere, right? I needed it to be trivial normal bundle. And trivial self-intersection. And so I'm claiming that I started with the TI and I did this modification and I got some SI. The SI is the algebraically dual sphere. By the way, I'm using the finite family version of the disk embedding theorem, which I did not state. So this is not a single disk necessarily, potentially many. So you have to, it's like trying to ignore that part. Mark asks, well, what about the framing? You have to check this trivial normal bundle thing. G was not framed. G did not have trivial normal bundle. That was part of my problem. But I'm using it twice. So T was framed. Clifford Torres, super nice. Look at it. Has the nicest normal bundle you can think of. And you're doing this modification. It's called contraction. You do this contraction, you're going to get this contribution from the Euler number of G, but you can fix it. How will you fix it, Mark? Or anybody else? Sorry,
Do it twice.
Sorry?
Do it twice. Like,
You are doing it twice, right? Because
yeah, but like their opposition, their kind of orientation or opposition.
That's true.
Algebraically, they should cancel.
at worst, it will be some even number thing. We know how to fix even number things. But I think EK is also right that it's like kind of an opposite situation. So you have like an orientation thing will probably tell you that it's like once you get Euler number, once you get minus Euler number. But in any case, you get it twice. So you can always fix it by adding more stuff. The other thing you have to check was this trivial self-intersection. The trivial self-intersection is also coming from the fact that you're using the disk twice. So you're just like, thank you, thanks, Dave. So you're going to like get trivial self-intersection. You're going to get this trivial signed count of intersections because of the picture Daniel drew yesterday. Because there are two copies. Yes.
If you end up with like the even number problem, couldn't that turn into like a feedback loop? Like you're going back and forth between like the problem one and the problem with the even Euler number. I forget which one that is. Like, how do you know it'll
Because I'm doing
happen?
a totally different thing. So this is like, now I'm in the Whitney disk world.
Yeah.
And now I'm trying to do something. Now I'm trying to find a friend for this W. And when I say fix it by doing this twisting, I mean you've changed your TI to some SI. Maybe the SI has some non-zero Euler number of its normal bundle. You can do this interior twisting to SI, and SI will like gain new self-intersections. It was pretty immersed already, so I don't care. And you'll fix its Euler number. I know it's written as twisting, but it's like the same procedure. So it's like, it's local to the sphere and doesn't interact with any of the previous things. I'm glad that you're worrying about this. That's exactly the sort of thing you should worry about. But in this case, it's fine. It's like, there are too many surfaces and spheres in the game. But like, that's happening over there, it's far away. I don't know if that helped. That helped. Dave has had a question for a while.
Just a small comment. I think one way you could package it and not use the family disk embedding would be to consider the representative of F with the minimal number of self-intersections and then show that that's zero by assuming that there's more than zero, do one Whitney disk to remove one pair, contradicting the fact that it wasn't more than zero, which gets rid of things like boundary Whitney disks and boundary Whitney disks. Might be hard.
But I'm trying to get rid of all of the intersections of F, right?
And so you take the regular homotopy of F, it has the minimum number of intersections, and you assume that it's not
The
zero.
minimum number of intersections of
So,
F
of
with
F,
this
yeah,
stuff?
but you want it to be zero. So you assume that the minimum number is not zero. And then if you could get rid of one pair using one Whitney disk, that would show you that that was contradiction. And so the minimum number is
I'm very confused by this because we're like trying to embed F, right?
Right.
Yeah, and so I'm
So-
trying to prove that the minimum is zero.
Right. So
Yeah.
assume that the minimum number is not zero.
Yes.
So if the minimum number was not zero, then if you had just one Whitney disk, you could get rid of one here, making a lower minimum, which is a contradiction, which means you don't need to consider more than one Whitney disk.
That feels a bit circular to me, but let's talk about that later.
Yeah.
Other questions? There are many hands. Yes.
Can you say again why we just get algebraically and not geometrically?
That's a great point. Maybe Dave brought that, other Dave brought that up. It's like this G, the way that I've drawn it here is a little bit misleading. That G could have, so G was in blue, that could have had green intersections like this. Shouldn't have used green, I'm sorry, that was Whitney disk intersections with G. So this should have been orange probably. Do you see what I'm saying? So when I'm doing this construction, the Whitney disk could have been intersecting that thing. But because I'm using two copies, it's like the extra intersections are algebraically canceling. So that's why I get extra intersections, but they come in these plus and minus pairs. So it's no longer geometrically dual, but it's still algebraically dual. Other questions?
Sorry, I just missed so you're compressing once, right?
Yes.
Okay.
Someone might be thinking about symmetric contraction. Are you? That is something you do often need, and that's something that comes up in the non-simply connected case because you want this algebraically canceling equivariant self-intersection number. And in this case, I don't think that works out as nicely. I was trying to avoid it to give you the simpler construction because here you just have to count signs.
You didn't talk
If
about
that-
that.
Oh, sorry. I don't know what I was talking about. Anyone else? Yes.
So in the statement of the disk embedding theorem, we needed a dual sphere that has trivial normal bundle and trivial self-intersection.
Mhm.
But we could always arrange that if it has trivial like algebraic intersection number by interior twisting. Was it stated like this because it's equally like different if it's like not simply connected?
The difference was because I wanted to consider the signed count of intersections, right? And we saw yesterday there was this formula relating the signed count of intersections, the Euler number of the normal bundle, and the homological intersection. So if your normal bundle is trivial and the signed count is 0, then the homological thing is 0. So in other words, in the case that you have trivial normal bundle, the signed count is the same as the homological count, but it's not always the same. So I wrote down the thing that I was gonna use. That was roughly the reason. So my goal was to only talk about that kind of intersection. And I have totally failed, but that was my reason for doing it that way. Okay. Yes.
What's the problem for just use the usual disk embedding theorem to remove one pair of intersection at a time?
You could do that. Then you kind of have to like, what do I want to say? Blanking on this right now, but the way that I would usually want to do it is like I would want to make my Whitney disks disjoint from one another. So if I have an embedded thing, then I've sort of fixed this all up like this, right? But suppose now I embed one Whitney disk, and I'm not caring about the other Whitney disks, right? So suppose I just use the version I stated for the disk 1 and do the Whitney move. That embedding that I found, well, I was only doing it in the complement of F. So potentially the embedding I found could intersect the other Whitney disks, right? Which would then, when you do the Whitney move, would create intersections with F. Does that make any sense?
But then I just do this whole procedure again. I find one Whitney disk and
You could put it that way.
okay.
That's possible. Another thing you could do is you know that the disk embedding theorem comes with a geometrically dual sphere in the outcome. So if your other Whitney disks intersect the embedded one, just tube into the geometric dual to get it off. So there are ways to use the single one multiple times. It's just easier to use the family one. Just use that one. The proof is really the same. There's no extra complication to proving the finite collection version of the disk embedding.
Does it have to be?
And I thought you would all let me do it. That was the reason.
Does it have to be a finite collection of disks?
Yes, to have an infinite collection of disks is infinitely harder. Talk to me about that later.
Is it true?
It is true in a controlled sense, in a technical term of the word, technical meaning of the word controlled.
Can we go back to why taking this claim solves our goal of why does making the intersections go away?
So the claim says that if I solve the 3 and 4 problems, then I find the nice Whitney disks. And these nice Whitney disks would kind of live right here.
Right,
And then I would do the Whitney move,
right,
and then I would embed F.
right.
And that was the goal. And I've done even better. I've embedded a sphere.
Maybe I'm a bit confused. Why does what?
F is in this class. So alpha is the class of F.
But why do we know that it's torus?
It's not a torus. This would be even better. This would be an embedded sphere. So I'm saying I can't possibly solve all my problems because otherwise I've stated a ridiculous theorem. So at some point I'm going to need to change it. I haven't changed it. The logic of the proof is, if I could have set this up, then I could have embedded a sphere. I'm trying to convince you of that. But I will not be able to set this up, at least not for a sphere. But then I'll have to modify my f into a torus. And then I'll be able to set it up, and then I will be done. So maybe 12, oh God. Try me again in 10 minutes. Wait, no, it goes till 11. Okay. Right. Demigod. All right. Can I self-censor as well? Thank you. All right. Hey, these are the two requirements of the disk embedding theorem. This is the proof of the claim. The claim says that everything, if I can solve these, the first one is free. So all of this was justifying that first row of the table. Okay. Now I want to stare at this table for a second. We had said like our goal was to be very clever, right? And the cleverness was like, I'm going to do this in the right order and try to solve all my problems. The first thing I do is like problem 3 is a kind of a silly problem. Just solve all of them by pushing it into problem 4. Yeah. Now I have problem 4. Change this word to uncontrolled. It was arbitrary before. I have no idea what that thing is, what the what the type 1 problems will be, but those are free, so I don't care. I can fix these by doing this tubing. Same for the, right. So I can fix these by doing this tubing. That will change the twisting number. I'm going to just ignore this one because those are free. And that's going to change the twisting number. So what I noticed is, well, right now I've solved 3 and 4 and pushed everything into 2. And in 2, I have 2 options, but the prices are very different. This one's free, because the cost is this free thing. This one's very expensive. So if I'm stuck here, I get stuck in a loop. That's why we should worry about these things. So this is worrying. What do I know? If I knew that this thing was even, then I know I can always do interior twisting. Then I would land in the claim hypotheses, and then I would win. Okay, so one situation in which I can win is when this is even. Let me write something down. Who did this? Just kidding. All right, so notice there is no obstruction, as in we can embed F if I'm asking for even more from my friend G. So for example, if I were in a spin for manifold, we have proven that you always represent any primitive class. Yes, spin and simply connected. I always assume you always get a spherical representative for any primitive class. But we can do a bit better. I'm doing this, like, how many times do I tube into my G? Well, I do it for every intersection of my Whitney disk with F. Do you see what I mean? Like, it has some number of intersections with F. In this case, there's 1. But if I knew that every Wi intersects F twice, then I'd be tubing into the G twice per Whitney disk. And then the twisting number would change twice by the Euler number, changing my sum even number. Then you can still fix it by interior twisting. So another win condition is if each of these is even, just by doing this tubing. Okay. Now, let me convince you. In fact, it suffices if the sum of all of these is even. So this is going to be another picture. This is something called a transfer move. Can you see down here? Is it? Thank you. Transfer move looks like the following. So everything is F in this picture. So suppose I have, suppose I only know that the sum of these intersections is even. So that means there might be some Whitney disks where you have odd ones. Do you know what I mean? Like it has to be even. There's some individual counts that are even, but the odd ones come in pairs. Arbitrarily can be paired up. Let's say you have two of these Whitney disks where the individual intersection with F is odd. So we're all looking at this picture and we're imagining the obvious Whitney circles, right? It's like this, looks like that. Don't use those, use these instead. That's super weird. What do I mean by this? I'm doing the picture I drew for the boundary push-off operation, if you remember. So I have my little mole that's like whatever the disk was here. It's just been pushed off over there a little bit, all the way until the other end. And same on the bottom. So I'm getting two new intersections with F. One will be there, one will be there. Okay, it's mind bending the first time. But you should imagine that there's a little tunnel right here where that disk continued on. There's a little tunnel on top and a tunnel at the bottom. If you draw the right picture, this will be very obvious. I have failed to draw a good picture, but there are some people nodding, so I'm a bit hopeful. Yeah?
Why do we need that the other has odd intersection?
Because what have I done via this transfer move? I've made things worse. So I had this intersection and I've created a new intersection. So what I've done is I've created two new type 4 problems and I've put them in the Whitney disks that had odd problems. So now they have even problems. And so I win. So I'm claiming this is supposed to prove that if you have this, then you can set up this by changing the precise Whitney disks you're considering. Karen was asking earlier about like, how are you pairing up the points and how are you choosing these arcs? This is a situation where choosing the arcs correctly is allowing you to make things worse in some sense. You're creating more type 4 problems, but you've changed the situation where you had some Whitney disks with odd intersections with F so that they now have even intersections with F. Removing intersections with F is hard. I can always add new ones by this. And so I can set up that I have this condition.
Maybe another way to say this is you apply number 3 forward ones and backward ones.
Yes. If I had just done this thing once, then I would have created a new intersection. And then I would have like changed it. So like when I did this first one, I wasn't fixing anything. Like there were no boundary Whitney intersections here. I created a boundary Whitney intersection and then I solved it.
Can you repeat like why we would win if each of these intersections is even?
Well, if each WI intersects F evenly many times, that means I tube into G twice for each Whitney disk. That means each twisting number changes by an even number.
Oh, that's easy.
And I know how to fix even numbers.
As a result of this move, the intersection of the first Whitney disk increases by 1, and then also the second.
That's right, because there's one intersection here and one intersection there. There's one for the top tunnel and one for the bottom tunnel.
So you're doing two moves, one on the first disk, another one on the second.
Sorry?
Are you doing two moves here or just one?
Well, it depends what is the move. Chu would say that we're really just doing boundary push off twice. Okay. I'm saying I'm doing the transfer move once. The transfer move creates two new intersections. And that one creates one new intersection. Do you know what I'm trying to
Both of
say?
the discs, not just one of them.
Yeah, I changed, like, this used to be like that. And I changed its bottom to go like this. I'm gonna draw the picture. So I had this picture. I had this picture. And you wanted these Whitney discs, right? These Whitney circles. That's the thing you would have obviously drawn. And I'm saying, don't do that. Do this instead. But that's weird. I've created a new intersection. Like, why did I do that one? There was nothing to fix. I just did it. Because of, I don't know, character flaw. But now I have this intersection. Now I fix it. I'm following Chuyu's method now. Now I can fix it by using the type 3 solution. So let me fix this by pushing in that direction. So both of those Whitney circles have changed. So over here, I have this tunnel on top, where this Whitney disk gets a little tunnel. So I get a new intersection on top right here. And then over here, I have a tunnel at the bottom, and I get a new intersection there. Thank you for nodding. Good. All right, I'm gonna self-censor. No, don't talk to me.
Quick question, can you just pose a better picture in the?
Yes, I'm trying to draw very nice pictures, but if you are drawing very nice pictures, then you could be really helping me out. All right. Okay, good. So, if we could set this up, we would be done by this long sequence of arguments. Sometimes we can't. And this is good because sometimes you don't get spherical representatives, okay? Like there are concrete examples of immersions of spheres where you can't solve this problem. So for example, you could consider the class 3 inside of Z, which is H2 of CP2. And you can represent that by an immersed map, a generic immersion of a 2-sphere. But you can never set it up so that these numbers are correct. There's no spherical representative of that class. And you can prove it in a way that I will certainly not tell you right now. Happy to tell you more about later. But remember, we're only trying to get a torus. So somehow like adding some extra genus is supposed to help me. So how will we do that? Well, I'm gonna just do it. There are 5 minutes left. Just did it right here. Okay. And I claim to you that I'm going to be able to win now. Why is that? I have my torus. The torus, very importantly, comes with these 2 circles. And I mean, I was being a bit glib. I really mean like a trivial stabilization of my sphere. So it's literally just a little. So these are circles that bound embedded framed disks inside of my 4-manifold. So there are these embedded disks bounded by these circles. And I'm going to do something that will seem weird for the next few minutes. So bear with me. As if that's any different from anything else. Okay. So now I have these circles, they bound these disks. I'm gonna make things worse. I'm going to, instead of having that be a disk, I'm going to like poke my finger into it to make it come all the way back to the surface so that I can change it into an annulus. So I'm going to set it up so that it like comes back down and touches my surface again. And same for this guy. Meaning that what I have right now is a picture like this. I've drawn F for you. There's an annulus. There are two annuli, A1 and A2. So I had my caps, C1 and C2, and they've now given me annuli, A1 and A2, that look like this. So F is showing up in this picture in two ways. There's like the line one, and then the flat one. And then this annulus is like, has its two boundary components on these two depictions. It's like a little portion of the annulus. There's my A for annulus.
Sorry, I missed out. Where does that two come from?
The two,
The two.
this one, I've poked my finger.
I mean the one you attached to F.
This one?
Yeah.
I've just added it.
I see.
I'm saying do a trivial stabilization and add a little embedded one handle to your surface. We haven't talked about stabilizing surfaces yet. That's like a thing you can easily do to surfaces. It's just like add a little thing.
We're trying to transfer F into a torus.
Yeah, so now it is an immersed torus. It's like the torus portion is very embedded. I just added it. You know, for reasons that will be clear soon. I've just added it for no good reason, it probably looks like. And now these circles bounded disks, and just by taking a little mini disk on that disk, putting it on the surface, I've made it into an annulus. Okay? That picture is suspiciously accurate. Now I have this set up. Now I'm going to make it even worse. I'm going to take this bottom sheet and I'm going to push my finger through it to create this new intersection and push it along in one of these fibers of this annulus. Push it all the way up. That creates two new intersections of F with itself. Yeah. Also, very accurate picture. There are these two new points of intersection. They come with sign plus and minus. And when you do this finger move, you always get a canceling Whitney disk, which is the fingernail Whitney disk. Kind of looking at it right there. So the correct thing for you to do would be to take that Whitney disk for each annulus and put it into your collection. Don't do that. Take the other one. Now you have to convince yourself that there is another one. Namely, well, there was this Whitney disk right here, the fingernail. But instead, I could consider the rest of this band. The boundary of that the remaining bit is a disk. There was like a bit of the disk that I removed a fiber, neighborhood of a fiber from an annulus. So a disk is left behind. I'm almost done, I promise. And the rest of it is a disk that pairs precisely those two points of intersection. Sorry, I'm not going to ask for questions. It's too late for that. So I get these two new self-intersections and Whitney disks for these V1 and V2. So let's call this V. So each annulus gives me a new Whitney disk. And I've made F more immersed now. So now we're going to consider my collection, whatever I had before, trying to fix everything up, union this V1 and V2. These disks are so nice. They like don't intersect F. They don't intersect the W's. Like those annuli were so far away from everything. They're just super, super nice in every possible way, except their boundaries intersect at a point. So this is like an amazing collection of Whitney disks with exactly one problem. So the only problem is boundary V1 intersects boundary V2 in a single point. Right there. This is great news for us because I've created one new problem. And that one problem I can solve with move 3. When I use move 3, I solve that problem. There's only price I pay is one more intersection with F. That's what I wanted. And then I thank you.
I was just clapping for winning, not.
So there might just be direct approaches to constructing locally flat surfaces. Tomorrow, I will talk about Alexander polynomial one thing. We'll probably not be able to talk about isotoping, like topologically and knotting I1Z surfaces to knots. Happy to talk more about that in person. But I'm going to stop talking. Do you have questions? More questions?
So C1 and C2 is chosen so that they intersect once?
That's right. I really did mean like, so C1 and C2 were these caps. So before the tubes, they were these caps. So I meant the boundary circles where I really picked the longitude and a meridian. And they intersect once precisely right there. Tomorrow there will be no pictures. I don't know if that's good or bad, but.
Is there specific obstruction on when do we need a torus and when do we need a sphere?
Yeah, sort of. So, something that's in the background of this story is, you can consider this value as an element of Z mod 2. You can see like you want this value to be 0, right? You're trying to make
What do you mean invariant value?
that's the thing I'm answering. You have to let me. So the thing you notice right here is that this count can depend on the family W, right? So I mean the way I've defined it, it's an invariant of F with the family W, but you really want it to be an invariant of F. And what we did, I mean, this result is by Lee and Mochinsky, but what we did in our paper with Daniel and Mark and Pete, which is where this proof comes from, is we gave a characterization of when this value depends only on F and not on the Whitney disks. It's a version of something called, you know what a characteristic class is? A class is characteristic if its intersection with every class matches up with that class's self-intersection. So it's a version of that. So for characteristic things, this will be true. That would be independent, but it's like a weaker thing called band characteristic. It's something that you can like compute based on all the homology classes. So what did I mean by that? Right, so if that value is 0, then you could have just embedded your original F. And sometimes it's well-defined, which means it could be either 0 or 1. And then if it's 0, then you win. And if it's 1, then you need to improve it. So there are precise answers like that to your question, but it's not so cut and dry. But there is a very explicit thing I can say. So you can use this approach to think about like surfaces bounded by knots inside of punctured simply connected four manifolds. And this exact proof shows you that in any simply connected four manifold, arbitrary knot will always bound a genus 1 surface. So the topological M genus for a knot is always less than or equal to 1, unless you're in V4. Okay, so not S4 surfaces. And in that case, you know that you only ever need tori in the CP2 or star CP2 case. So if you give me a more controlled problem, this answer has gone on way too long. So sometimes yes, sometimes no. Sorry.
So from what you just said, will it work all the time, always spherical representation when it's a characteristic class?
When it's a characteristic class, this will not depend on the W's. Meaning that this is some invariant of F and the family W. But potentially it will change, when you change W, this thing might change, right? If it's band characteristic, which is what we defined in this paper, value does not depend on W. If your goal is to embed, then you want it to be ill-defined. Because if it's ill-defined, in particular, it means there's some Whitney disks for which it's 0. Because that's how you win, right? And in fact, what we have shown is that when you have a torus, when you have genus, then it's ill-defined because you got to change the number and then you win. So this is a situation where you want it to be bad. You don't want it to be well-defined. It's also a long answer. Sorry.
What about in primitive class?
That's another great question. We needed the primitivity to get our friend. And the friend has been just like the best friend, right? Like friend has been there for us throughout. So in this geometric argument, we really, really needed this dual sphere. And having this class that's dual in this way, that's essentially the same as being primitive, is the same as being primitive in a closed form manifold. Lee and Wojcinski don't need this, so their proof uses more surgery theoretical techniques. And so for them, they consider non-primitive classes. But for them, they really needed pi1 of the complement to be abelian, and they needed all of this other stuff. We're not worried about that. We can work in arbitrary good group, good fundamental group for manifolds, but we really need our friend. So if you want non-primitive classes, you should look at Lee and Wojcinski. If you want more general for manifolds, you should look at our. This is the unique intersection of our two theorems. Should I self-censor because of problem session? Thank you. Thank you.